Good evening, all of you, respected INS members and friends. I am once again delighted to welcome you all to today's webinar, and uh, I have particularly received a lot of good feedback from the viewers, both online viewers and offline viewers, regarding the INS webinars for its content and coverage of wide range of topics of current interest. Encouraged by this, the committee endeavors to keep this activity very regular for the benefit of online viewers and for those who view our YouTube channel on our INS website. Today's speaker is our own member, Dr. R.K. Singh, Ram Kumar Singh, a distinguished scientist who has made lasting impact on varied fields through his expertise. I am sure you all remember him for his high-end work on the modeling of tsunami and of SWR containment model for limit loads. On INS and on my own behalf, I welcome you, sir, to our today's webinar on this very important topic of tsunami hazard assessment of Indian coastal nuclear power plants and other facilities. I sincerely thank him for agreeing for my request and to give a talk. He could not say no to me because he is my first colleague in the office and my guru in many ways. We have worked together in hall number 7 on some projects and also on some international meets. This is an important topic for us, no doubt. We know how devastating it was in our eastern coast in 2004, much before the famous Fukushima in Japan. Numerical modeling of tsunami is still an open challenge, especially when it comes to estimating the forces in the tsunami shore interaction. We'll do the modeling in 1D, 2D using shallow water equations to assess the propagation of tsunami in deep oceans. Though this is well established now and matured, there are many challenges when the impact of tsunami on offshore structures is to be estimated. The fluid equation, namely the Navier-Stokes equation, is widely used by the researchers. There are also efforts to model the combination of earthquake and tsunami to simulate the large-scale dynamics in open sea though there are many challenges to couple these two. All this calls for a high-end computation, refined grid, and real-time assessment using multi-scale modeling. With the advancement in this field of computation in the near future, I think it may be possible to model and run the tsunami model even on a laptop. So Dr. Singh is going to talk to us on more of all this. So before I invite him to start his presentation, I would request our President, Shri S.K. Mehtaji, to give his opening remarks.
Well, thank you very much, Dr. Rao. And I welcome Dr. Singh, my old colleague, taking up the topic, which is very important. It was not known before Fukushima, but gradually its importance and analysis has grown up. A lot of work seems to have been done in the direction to understand and how it should be handled. And I think I'm looking forward to learning more from this lecture. Welcome.
Thank you, sir. I have to formally introduce our speaker today, but then it's really not required, but to keep the records in place. The YouTube, people will be seeing this YouTube many years to come now. So for the record, whoever listens to our YouTube, I have to read out his resume. Dr. Ram Kumar Singh, distinguished scientist, has been associated with the Department of Atomic Energy as Rajaramana Fellow, former Associate Director RDDG, and Head RSD in BARC. He has worked on Indian nuclear and power reactors and research reactor for development and safety assessment with a team of nuclear engineers and scientists for structural mechanics, thermal hydraulics, reliability, and safety evaluation of nuclear reactors and other facilities for the design beyond design basis accidents and other strategic applications. A significant number of planned projects have been executed under his supervision in addition to the collaborative projects with academic and research institutions. He has successfully coordinated standard problem and round-robin exercises backed up with mega-scale indigenous experimental programs supported with computational experimental studies related to nuclear reactor and safety problems. The RK Singh has guided a large number of PhDs and MTech students in IITs and ISCs and HBNI. Dr. Singh has been recognized as a senior professor in HBNI and post-superannuation has served as visiting professor of IIT Roorkee, IIT Mumbai, IIT Bombay. He continues to provide his services to the Department of Atomic Energy and AERB as expert consultant on concurrent nuclear safety issues and activities related to revision of AERB codes and standards, besides mentoring young engineers. Dr. Singh is actively engaged in national scientific and technical committees as expert for review of projects of relevance and importance. Dr. Singh is a fellow of Indian National Academy of Engineering and a member of Indian Nuclear Society, Indian Association for Computational Mechanics, and Indian Society for Heat and Mass Transfer. He is a recipient of DAE Homi Bhabha Science and Technology Award in 2011, and more than 3 Group Achievements Award. So he has published 117 international. He has published in 217 international journals. He has 8 books. He has published in 241 international conferences, 101 national conference, 33 BRC reports, 9 restricted reports, including the one where he worked with an institute in Karlsruhe, Germany. So this is the very enviable resume of Dr. Singh. So it is now my pleasure to invite him to start his presentation. Dr. Singh, you can start your presentation.
Thank you, Dr. Rama Rao. I hope I am audible to all the audience.
Yes, yes.
Thank you. And first of all, I thank Dr. Rama Rao and the Indian Nuclear Society, the President Indian Nuclear Society, Mehta Sahab, and all the familiar senior colleagues who are present here, Mr. Sanat Kumar and Mr. Dharme and others. So I will start this presentation, Tsunami Hazard Assessment of Indian Coastal Nuclear Power Plants and other facilities, where many organizations have contributed, because this exercise we did for the Indian National Warning System to start with, following the 2004 tsunami event. So immediately there was a requirement, national requirement, to have the National Tsunami Warning System in place that was being managed by IMD and Ministry of Earth Science. And since BRC was doing some modeling work, so we were called up to identify the sensor locations for the warning system, and I will give some details about that. This was followed by the evaluation of the various coastal sites. And as you may recall, in 2004 tsunami event, the Kalpakkam site got inundated along with the colonies and other areas, and there were some tragic events. And also there were requirements to evaluate and look upon the various coastal facilities which were coming up in various parts of the India, particularly the coastal sites. Slide is not moving. Okay, yeah. So now, following this 2004 event of tsunami and 2011 Fukushima event, there was an importance attached to the extreme events in addition to the conventional requirements of core cooling in the reactor safety. So that was one new challenge that was thrown up to the thermal hydraulics people. And in addition to the decay heat removal, other issues were there, like the effective hydrogen management that was to be ensured following large earthquakes, tsunami, flooding, and fire in case of a station blackout. There is a MIT report that describes the various considerations like emergency power following the beyond design basis external event, then emergency response in case of the beyond design basis external events. Then importance of containment was attached not only for the internal event but also for the external event. Then hydrogen management, spent fuel pool, and all this has to be done with regard to the specific plant siting and the layout. Now in this case, there was a requirement to have the multidisciplinary approach for solving this problem, unlike the conventional thermal hydraulics where people were only looking at the reactor core. And all these thrust areas subsequently were addressed at BARC, and following that many participants joined from the NPCIL and the Atomic Energy Regulatory Board. So basically thermal hydraulics, structural mechanics, it's a strong link to the seismic and geological engineering, combustion and fire engineering, environmental dispersion problem. All these became very prominent areas of work. And besides all this, if the plant has to operate, there has to be a sound engineering practice. Now this, everybody knows this 26 December 2004 tsunami event. This caused the problem of inundation in the nuclear facility at the Kalpakkam MAPS reactor. And also the Bhavani site where the containment raft was being constructed, that also got affected along with the neighboring township area. The Safety Research Institute and the IGCAR, they started this on-site data collection because immediately after this 26th December, the following day, 27th December, they started collecting the data of the inundation and the damages that took place. Some overall survey was taken up by them, and also some modeling activities started. And as I mentioned, BRC was asked to participate in the tsunami national warning system because that time it was a national requirement to have a national warning system. Before that, even 2004, there was no warning system. Only some tide gauges were there to monitor the tides, sea tides. So there was a backup of the in-house code development and the associated numerical activities, numerical modeling activities. Following this participation in the national warning system, we also looked upon the various DAE facilities, and main importance was attached to the existing site Kalpakkam, then on the west coast Tarapur site, because on the west coast, as we know, there is a 1945 event in Makran, 8.1 magnitude earthquake, and also the Vizag site was upcoming. So all these three sites were evaluated for the local inundation mapping. Besides that, also all over the Indian coast, we did some survey, and from the modeling, we could get some data for the upcoming nuclear power plants, which are still in the pipeline, like the Pati Sonapur or the Haripur, Mithi Virdi, and so on. So basically, as I mentioned, that this was a new interdisciplinary area that emerged and which was important for the tsunami considerations. And later on, this was also effectively utilized for the thermal discharge problem, environmental dispersons, and so on. And we could get good support from the NPCIL, AERB. And recently now a new standard is coming in AERB where many of these requirements are in place. So we started this work in 2005 with an in-house code development. As Dr. Ramarao already mentioned, the Navier-Stokes equation, but a lot of simplifications are required because the size of the problem is very huge. Means thousands of kilometers are to be simulated. So whether one should go for a one-dimensional or two-dimensional or a three-dimensional problem. So I will just give some flair of it. So we have basically this continuity and momentum equation. Then we have this free surface boundary condition for transportation of the gravity wave. Then somewhere the boundaries have to be truncated because as such this is a global tsunami. Of course, nowadays with the national warning system, they have global models where they simulate everything, but then it takes a lot of time, and particularly as the tsunami is progressing, one has to focus on the local area. So from that consideration, you have to curtail certain boundaries, and that is known as the Sommerfeld radiation boundary condition or the non-reflecting boundary condition. That means a tsunami wave which is going, it will just go out. It will not reflect back. Since that area is of interest, so we are only limiting to that. And of course, there is a coupling of the seabed as the submarine earthquakes happen. Then in that case, there is an upliftment of the sea bottom, and that has to be coupled with the ground acceleration data. So the equation number 5 takes care of that. So we started this work, and at that time only the tsunami wave arrival time and the height that were available through the various site surveys by the scientific community, many of the IIT professors, the IMD, the Ministry of Earth Science, they participated, and these data were available. So we could predict this arrival time and the wave height at different locations like the Sri Lankan coast or the South Indian coast effectively and in comparison with the reported studies. Then in the model, we had also these small islands like Andaman and Nicobar, and there also we could predict the tsunami wave height and the arrival time in agreement with the data. And these were given to the IMD and the Ministry of Earth Science for considering the warning system. Now, apart from this, there was also a data available from the JASON-1 satellite. On the left side, you see the picture where the blue line is showing the direct arrival of the wave. And here you see a small island, Sri Lanka, and then this is the South Indian coast. So this was also consistent with our model that you see here on the right-hand side. And once we have this Sri Lankan small island, in that case, there were also effects of the wave deflection that could also be predicted in our model very effectively. So this data was given, and as I mentioned that there was no tsunami warning system that time. Only we had a number of tidal stations, tide gauge stations at various coastal sites like Paradip, Vizag, Chennai, Nagapattinam, which was heavily, of course, this sensor got damaged at Nagapattinam. Then on the west coast also we had some locations like Koshi and other locations, Okhla and so on. So this data was made available later on, means I think this came in 2007. That time this data also was not available. So later on we compared our predictions with this data, and they were also found to be in agreement. And these are some of the frequency time plots for 3 days, 26, 27, 28 December at various tide gauge locations. These data were available and we could compare our results. Then later on in 2007, as I mentioned, because there was an international effort, and this data was collected not only from the Indian census, but also globally everywhere, because this was a global tsunami. So this data which was available, that was published in 2007. And by that time, almost our Indian national warning system was getting finalized. But to our satisfaction, we could see that the different wave periods that we computed after taking these signals, we computed these data, and we could clarify that they were also consistent with the detided gauge data, because these were the tide gauges, and for the tsunami wave we have to detide the data, so there is some filtering required, and that was done by this one gentleman Rabinovic in 2007. And particularly if you see this some reflections which are taking place from the Sri Lankan coast or the Nicobar Island, in that case also these results were available. Now in this case we could also justify that the two-dimensional surface wave modeling is sufficient, because our locations are far from this source of the tsunami, almost 1500 to 2000 kilometers. Only for small islands like Andaman and Nicobar, there is a concern because they got inundated, and in that case some special care in the modeling, local modeling is required. So another example is here. This is for the Nicobar, and here also the time signals which we captured, they were consistent with the recorded information. Of course, in Andaman there were two gauges and one of them got damaged. Then after getting satisfactory result, this is the data from the Sri Lankan coast, and again we find some reflections, and they were also in agreement with the recorded data. So this also gave good confidence for the modeling of tsunami and locating the various sensors, because that time there was a massive plan for the national warning system, that in addition to this tide gauge data, we should have bottom pressure recorders and other monitoring stations at various locations in the Indian coast. So after this, there was an effort to evaluate various nuclear power plant site, and Kalpakkam was chosen as the first site. Of course, we did this evaluation for 3 sites, Kalpakkam, then on the west coast, Tarapur site, because for the Makaran that is relevant, and also the Vizag site that was upcoming from the BRC Vizag facilities. So that was also evaluated, but I will focus upon in this talk only on the Tarapur and the Kalpakkam site, because that was a repetitive exercise. So we invited many participants from the different academic and research institutes like IIT Madras, then this Ministry of Earth Science, ICMEM, now this is known as NCCR in Chennai, then NGRI and ACRI. And besides, we had our own participants from the BRC, NPCIL, and ARB. They also joined hands, and we did this work. So the first task was to identify what should be the kind of grid, and for that we had support from the National Remote Sensing Agency and NCCR, Ministry of Earth Science. So they collected the data at very fine interval of with an accuracy of almost 0.35 meter, with a geomorphology and bathymetry grid size of about 50 to 90 meters, because in the open literature that time only, I think, very crude grids data were available. And then of course, finally we had discussions in this committee on the uncertainty estimations, like what should be the input, what should be the influence of storm or the Coriolis forces. And in addition to that, there are many complicated site locations, like there are creeks, jetties. I will come to this when I show you the Kalpakkam result. So the other important aspect was that normally the simple model of the sea earthquake is a single static bottom displacement model, but later on it came to our knowledge that this was a long rupture that took place and there was a finite time involved. So we developed this 5-segment model after discussions with various experts, and these are the different fault parameters: the length, width, depth, dip, strike, and rake and slip values for this 9.3 plus magnitude earthquake. And this was implemented in the model by all the round robin participants. So one requirement was that they should have this multi-segment fault model in their codes. Then on the west coast also we experienced, during the comparison of our own code and the Tsunami N2 code that was very popular, and this again we simulated this Makaran 1945 event with magnitude 8.1, and we got good results because very little data is available for different sites in Gujarat and Bombay. So we developed some important strategy and the steps for the tsunami modeling, because the design tsunami finally should address all the uncertainties of the tsunami hazard assessment, and it should be possible to look upon the past historical and possible future tsunami events which can take place in that region. Unfortunately for the Indian coast, this data is very limited. Of course, later on, lot of studies are done, paleo-tsunamic studies are being done, and international bodies also have been now taking interest. Subsequent to this tsunami event, some of you may remember that some additional events took place, which were later on 28th March of magnitude 8.6, then on 17th July 2006, again 7.7. Then again on September 12 and 13, two events took place in 2007, 8.5 and 7.9. So all these earthquakes were more than 7 magnitude, and they could be tsunami-genic. And these had been analyzed for the inundation model and the for the Kalpakam side. So now, fortunately, the national warning system is in place in 2007, and all the events are being recorded very regularly. And I will show you one example at the end of this talk. So there was a need to assess, apart from the various coastal locations of India, our own facilities, and that's why this effort was made. So we started this work, and meanwhile, it took almost 3-4 years. This Japanese event, Fukushima event, also took place in 2011, and there was also a requirement to fulfill our commitments for this safety, and we proceeded with that. Now, with regard to the instrumentation, I will show you this one additional example which was analyzed just to suggest the national warning system people what are the probable locations and what kind of sensors they should use. So this was a hypothetical simulation that was performed for this Parkfield, California earthquake, where actually this is a through depth model. That means apart from the surface wave which is propagating, it is an axisymmetric model, and there is an earthquake that is assumed here, and then how this is propagating almost up to 2200 kilometers. And this exercise was basically done to understand the nature of the waves that propagate at the sea bottom, because many sensors have been put, bottom pressure recorders have been put in the around the Indian Ocean. So we should understand its characteristics. So this example shows the tsunami wave propagation at the free surface as well as the acoustic wave propagation or T-phase wave propagation. So if you see here at the source location, basically we have this amplitude hydroacoustic frequency, which is about 2.8 to 3 hertz, which retains its characteristics at the surface top also. But apart from that, because of the bottom surface displacement, a long wave is also created in the range of 0.08 to 0.1 hertz, and that travels on the surface, that causes most of the damage. But we recommended that apart from this tsunami wave monitoring at the tidal locations and also at the coastal sites, we should also have bottom pressure recorders, because these bottom pressure recorders, they can monitor the T phase, and many acoustic sensors and acoustic modems are now in place in the national warning system based on this recommendation. So as the waves propagate, this T phase monitoring becomes very important, and that was one conclusion. And this waves T phase travels almost an order of a magnitude faster than the tsunami wave. So that is the advantage, that one can actually sense these waves at the sea bottom, and then through some transmission it can be communicated very fast. So this was shown at the seabed. This is the kind of amplitude, and if you see the top, so there is a long wave of this magnitude, but here this acoustic wave becomes very weak. So some sensors can be placed at the sea bottom. That was the conclusion we draw, and this is not new. Now I think many countries are working on this very effectively. So most of the bottom pressure recorders and the acoustic modems, they were proposed from this study to the national warning system people in the Ministry of Earth Science, and they could effectively utilize this information for monitoring purpose. This is a typical arrangement from the NOAA. They have this arrangement where they have this bottom pressure recorder, and then they sense this, and through this satellite communication, they can communicate very fast, and they can give information or alert to the plant people and so on. So that was the advantage. So coming back to the modeling, now we had various institutes like IIT Madras, then this Ministry of Earth Science, ICMEM, now it is called NCCR in Chennai, then NGRI, National Geophysical Research Institute in Hyderabad. Then of course we had our own partners IGCAR and ACRI, and later on AERB and NPCIL, they also joined. And these are the various codes which were available with various participants for doing this study. And these are all standard codes which are being used internationally. Besides, we had also our in-house codes, and we proceeded with the work. So we actually provided the refined bathymetry and land morphology data that we got from the support of NRSA and NCCR, that is under the Ministry of Earth Science, to all the participants for Kalpakkam, Tarapur and Vizag side. And then we started with a benchmark example. And once the codes were verified, calibrated, of course, there were some specific benchmarking issues. Then we also asked them to work upon the inundation model, because there are two phenomena which are to be known. And that's why we have to do a global modeling, and then we have to do a local modeling. That means if you want to study a local site like Kalpakkam, or let us say Vizag or Tarapur, in that case, we have to have a very fine grid, and that we got collected from the NRSA. So for the comparison purpose, we identified that, okay, means first all the participants must give the data at 100-meter ocean depth, because in the deep sea, where the sea depth is of the order of 3-4 kilometers or 5 kilometers, the waves are traveling, and once they come near the shore, they dissipate most of the energy. So the first point of comparison should be at an ocean depth of 100 meters. And then from following that, we can have a local and global interface model. That means common point of comparison. If that is satisfied, then people should go for inundation modeling and do the calculation for the local run-up. So this basically has a multi-grid model arrangement, and this also suffers sometimes from the dispersion and the phase errors, the waves numerically, because means you are discretizing the domain, and in that case there are some numerical dispersion and phase dispersion errors. So we try to minimize that through these techniques, multi-grid models, and we try to calibrate that. So in this case, the benchmark problem, one typical I will explain. There were some 3-4 benchmark problems. So this was an example of a strong earthquake in Japan, in Hokkaido Sea. And this resulted in extreme tsunami. The maximum run-up was almost 32 meters. This Monali village almost got washed out. And this example has also been verified with a small scale laboratory experiment, where these in a large scale tank by the electric power industry in Japan, and they have conducted this experiment. So we gave all this bathymetry data, the boundary conditions and the input waves, and output was the temporal water surface variation at different locations that were to be given. So this is the input that is given to this model. So first they carried out the experimental verification, and then they did the analysis for the Monali village, and that was found to be in good agreement. So all the codes got calibrated, and here you see the different instruments which are put, the gauge data and the numerical model, they were in reasonable good agreement. So this is the layout of the national warning system that we proposed, and many of the bottom pressure recorders you see here, they have these modems, and through that they can transmit. Besides that, we have also some coastal stations where now the tsunami warning is issued after getting the data and integrating and collating that. And then we have already this tide gauge data at Vizag and some other at Chennai and so on. So with all this arrangement, now the tsunami warning system is in place, and this got commissioned in 2007. And after that, there was an event of submarine earthquake that got recorded by this warning system. I will explain about that at the end. So before going to that, I will like to show the comparison of the various codes at the bottom pressure recorder location, because we had asked the participants to give the values of the run-up at different bottom pressure recorder locations, because they are being sensed by the national warning system. And you see that in most of the cases, the average run-up, which was predicted by various participants and as observed during the measurement, they were in agreement. And this ratio of the standard deviation and average run-up was also reasonable, in the sense that in most of the cases, and sometimes we had to also do some filtering, means some outliers were there, so that we had to remove. Then we asked the participants to predict the tsunami wave run up at the coastal sites, because this is from the global model. So Mumbai, like, although this is for the Java Sumatra earthquake, but we had in the model all the locations of Mumbai, then Tarapur and so on, because for the west coast these have become important. So we had a comprehensive model to do that. And in most of the cases you find that the comparison is reasonable good, with 17-14% error or variation among the various participants. Then similar thing for the Kalpakam, then Kudamkulam, and the forthcoming sites like Haripur, Patisonapur, Mithivardi and Kovada. All these locations we had carried out this comparison, and that is available with in a report form to various agencies. Now, apart from this, we had also this comparison at the standard tide gauge locations at Paradip, Vizag and Chennai, and they are also within 20 to 23% error as compared to the measurement. So after getting satisfied with the performance of all the codes that the various participants were using, we tried to see in detail what should be the kind of acceptance. And normally we see that the standard deviation to the mean was in the range of 2 to 25%. In some of the cases, yes, the comparison was not so good, but we accepted that considering all the limitations and the time that was available. So now in case of Chennai tide gauge, if you see, there the comparison is very good, because most of the participants, they had very fine grid near Chennai, because their focus was on the Kalpakam side. So because of that, here you see the agreement is good. So if I say 25% error, this is not because of the error or any difficulty or any problem with the code. It is basically the grid problem. But since our focus was, so now they have a good arrangement that they can take a refined grid at any locations and they can predict very accurately. And in fact, in the national warning system, moment an event, C event takes place, they start running the course grid code, and they start giving the warning messages. And later on, as the wave propagates, along with that, they predict that, okay, these are the run-ups, and people can take early action at various sites. So again, if you see the comparison at the standard locations, I talked about the 100-meter sea depth. And in that case also, in most of the locations, the various participants, they predicted the results of run-up in close agreement, almost 11 to 19% range. So this I am now showing you the inundation prediction at Kalpakam site. There are 5 locations near the security gate, Kokila Medu security gate, I1, I2 location. These were identified by us, where the measurements were taken by SRI. Then backside of the fire stations, I3 locations, behind the swimming pool, I4, and then Central Avenue, I5. And these are the values of the inundation reached. The water reached up to about 312 meter, 241 meter, 217 and 233 meters. So these are the site measurements that were made available. And we saw that most of the participants, they predicted, some were poor, some were good, but inundation prediction is very, very difficult even now today. because you need again very detailed land morphology of that particular site, and that time again the computers were the the powers of the computers were limited, but we got satisfied with this in the sense that at least they have calculated some results are good, some results are poor. So inundation mapping was not so good in this case. At some locations, yes, we could get good results, but the wave run-up was mostly very good. So wave run-up is the first criteria or first input that you require at various locations. So now here is the picture for the wave run-up, and there are 8 locations for the wave run-up: R1, R2, R3 up to R8. And these are the locations: Edward Bridge water intake at the maps where the plant got affected. Then CISF barracks, Gammon quarters, that time Gammon was working there, Sadras Fort township area, and Bhavani soil sample storage building. So all these locations we tried to, and these measurements were taken at different locations of the run-up. Watermarks were seen and measurements were taken by the SRI people. And this comparison was very good among various participants and along with the measurements, and in most of the cases the deviation was very, very small. So the run-up prediction capabilities were very good with various participants, and these are again some other run-up predictions at different areas. So these are the run-up predictions, and again you see here that in most of the cases the results are within 14 to 30% or so, and they are reasonable among all the participants, and even the standard deviation to the mean ratio also is good. So the observations or the conclusions that we could draw from this is that the inundation mapping is slightly more complex because you need more detailed local information, and particularly let us say if there are some backwaters, Sadras backwaters, or land morphology is complex, in that case there are some grid interpolation errors, and in those cases you need more detailed information. So that was one conclusion we could draw, but in most of the cases the code capabilities as far as the run-up is concerned was very good. Then later on we could identify these problems of improved source model with the multiple segments, and Kalpakkam site became the first site that got qualified for the analysis, and later on we took additional work for this other sites like Tarapur and the Vizag sites. Then we had also some opportunity to do complementary work in IAEA, and they had some codes which they had made available to all the participants, and this was again used for Chennai and Kalpakkam site. And here you see basically the wave heights, they were in good agreement. Similarly for Kalpakkam site also, and again for Vizag site we could predict that. And in this case we had different sizes of the grid, A grid, B grid, C grid, and in this case again we found that in most of the cases the comparison with the tide gauge data was very good, and we could get good confidence and insight into this tsunami modeling. So subsequent to this, the work for the western coast power plants started, keeping focus on the Makran 8.1 event, and this was also important because here again there was difficulty because this is a very old event of 1945, 8.1 magnitude, and here the data availability is very poor because no records normally are available in this case. And this subduction zone also is very complex. One side we have a very shallow subduction zone, one side it is a deep. So this distinction between the global and the local models were also quite challenging, but I was happy to see that most of the participants, they could predict this after the good experience of the Kalpakkam simulation. So now in this case, again, we had similar comparison at the various important locations on the coast of India, starting from on the west coast, mostly this Trombay site, Mumbai, Tarapur, Jaitapur. Then also we had included these eastern sites also because it is a global model. So here, of course, the Kalpakkam and Vizag, these values are very small because this event is on the west coast. Then we have some sites in Gujarat, and then of course some eastern sites at Haripur, because we included all the forthcoming power stations in our models. And so with this approach, we could get again very satisfactory result with regard to the prediction. And so these are some of the comparisons of the wave run-up by various participants, and they are almost in good agreement in most of the cases. The mean value and the deviations, you can see if you draw the mean value, the deviations are small, and this is what is shown here. So this got then we had also this local run-up modeling for the Tarapur side from the local analysis for the 1945 Makran event. And in this case also we had the results from various participants at the identified locations, and they were also in reasonable alignment. So this is the Tarapur site where there are some standard locations for comparison, and again the comparison was good. So then we moved upon to the another work after this with regard to the Kudamkulam site, because that time also questions were raised on the Kudamkulam site, and this Kudamkulam site is located in a location where both the events, the Java Sumatra event on the east coast and the Makran event on the west coast, both are important. So this was analyzed first for the 9.3 magnitude earthquake for the Java Sumatra source, and later on some work was also done for the hypothetical earthquake of 9 magnitude, because that time 9+ magnitude earthquake was in focus. So some questions were asked, suppose say Makran also gives an earthquake of 9 magnitude, then what will happen? So we did this work and we made some comparison of the run-up, and we could get the satisfactory result, and some inundations were mapped at the Kudamkulam site during this event of 2004, and we got the results in agreement with the. Now I'll come to this important tsunami observation that has given us some good strength. So this event was recorded by our Indian National Warning System by Inquest Hyderabad, and these are the values which are given at Chennai, Vizag, Ennore locations. So this happened in 2012. So because of these limitations of the limited historical data, after placing this national warning system, all these events post 2004 tsunami, like 28th March 2005 of 8.6 magnitude, or 2006 event, July event 7.7, then September 12, 13, again 2 earthquakes 8.5, and so all these are tsunami-genic. So later on we could analyze this, and the inquest could predict this within 8 minutes. That means 14-16 hours they announced that some tsunami is going to come, and they issued the alert. And initially this magnitude was estimated as 8.7. Later on it was revised based on the refined calculation as 8.5. So all the alerts like SMS, fax, emails, they were promptly responding, and the bottom pressure recorder, all this data and tide gauge data, they were coming. Apart from that, the maps Kalpakkam also had their own local monitoring station, and they also got alert, and they of course had received the information from the national warning system. So emergency response and the precautionary measures, all these were in place, and all the as per the operating procedure, it got initiated, and readiness of all the systems, safety systems to handle the probable tsunami was ensured, and nothing happened. So I will like to just summarize my talk. We have been able to carry out intensive code benchmarking exercises accomplished with detailed data collection, because data collection is very, very important for carrying out this. And of course, this should be supported with the instrumentation. So data collection is with regard to the refined bathymetry, because you need, nowadays people are using 10-meter grid also, and lawn morphology data. So this data is very, very important. Then of course, all the sea events must be carefully examined, and they should be carefully monitored. And this national warning system effectiveness has been shown, although there were queries from NDMA many times, some sensors have not been working. So this is also one important aspect, that all the sensors must be attended to properly, and data should be coming properly for giving early warning. For the Kodamkulam site also, we could see that the maximum wave run-up was 2.76 meter. Although at a remote distance, about 2 kilometer, 4 meter run-up was also observed. Now, in case of the two sources for the Kodamkulam site, the Sumatra earthquake source and the Makran, they are almost 1200 to 1500 kilometers. So they are far away from this plant, unlike the Pacific Tohoku earthquake of March 11, 2011, that affected the Fukushima plant, because in this case, it was almost around 200 kilometers. So it was a very near shore event, unfortunately, and that caused problem. But we have to again get alarm for the Andaman Nicobar and those sites, and some locations near Chennai where some reflections from the Sri Lankan coast can come. So those are the important points. Then we could also do work for the Jaitapur, Kovada, Haripur, Patisonapur, and Mithivirdi. At least from the global model, we could predict what is the nominal value of the wave run-up. Of course, more work will be required for the local site evaluation in terms of the data collection, then plant layout and so on, because finally how the wave run-up takes place and what is the inundation risk, that is also important for the layout. So this, I think some work has been done in AERB, and I believe that it will be continuing. Then DAE made a detailed assessment of external events as was highlighted in the AERB Expert Group Committee Report 2011 and the National Report 2012 that was submitted to the Convention on Nuclear Safety. And the actions taken for the Indian nuclear power plant subsequent to the Fukushima accident was presented, and it was appreciated. So I will again emphasize that the safety upgrades for the plants as far as tsunami is concerned, they are in place, and a thorough reassessment has been done for all the existing plants. And for future plants, of course, as I said, more work is required to be done. Besides this, I also would like to mention that apart from the national warning system which is in place, we have to also do some local monitoring, as we experienced during the Madras plant from the submarine earthquake event of April 11, 2012, where also there were some data coming from the local monitoring stations, and that got good confidence. So these are some of the conclusions and the lessons learned from this study, that tsunami evaluation for Indian nuclear power plants is important, and that we could do. Of course, I will repeat that again, it is just a repetition that local bathymetry and land morphology data, then past historical paleo-tsunami records are important, and this needs thorough numerical code validation. And nowadays people are working on the tsunami hazard assessment, just like the probabilistic earthquake design. There is a new discipline that is emerging, tsunami hazard assessment, probabilistic tsunami. People are working in these areas. Of course, you need a backup still for a deterministic analysis from these codes, and then only you can go further for the probabilistic codes. Then near shore earthquakes are of special considerations, particularly there are some faults near the Andaman and Nicobar site. So they have to be again taken care of. And most important is that redundancy in instrumentation and regular calibration, because many a times we have observed that the sensors are in place, but the data is not available. So this has to be, again looked by all the stakeholders together. Thank you.
Thank you, Dr. Singh. It was a wonderful presentation and a lot of information in this presentation. We may take a lot of time to digest this. Now, may I request Shri Dharne to take over for question answer, please?
Yeah, sure. Thank you, Dr. Singh. I mean, you made it so simple, but most of us know that it is not so simple. The tsunami modeling and the prediction, hazard prediction due to the tsunami is not so simple. It has got a lot of complication because of the natural factors, because of the grid differences between open sea as well as coming to the shore, the bathymetry availability, the data availability, and so many things. But we must say that DAE, and in particular your group, has done a fantastic job in it. And now we will be reaping the fruits of it. So thank you so much for a difficult subject made so simple for us to understand. Thank you so much.
No, Mr. Dharne, I must compliment and thank you, because of your participation. We could also get many insights from the different code users, and from your expertise. We could fine tune our work during this many meetings that you gave very, very positive feedback to the participants. And fortunately, in this case, the AERB and NPCL also joined hands at a later stage, but everybody was together, and in IAEA as well as in all these exercises. And we could do a lot of work. At least we could, qualify our plans, and we could at least, present to the international community in a very confident manner.
That's a great achievement, actually. The reassurance of the faith that, well, the plants are safe is most important, nationally as well as internationally, especially in this era where people are against nuclear. So that is quite important. So I would now like to request participants, whether there are any questions. Dr. Singh will be very glad to answer it.
Three people have raised their hands. Avanish, Sanat Kumar, and
I will give first to Mr. Sanat Kumar.
Yeah.
Thank you, Dharne, for getting me first. I completely agree with Dharne's summation that Dr. Singh's presentation has really given a very good thing about the tsunami preparedness. Prediction, that is more important. That is, models are working. That's fine. Now, I have two questions which I will ask, but as usual, I am not very sure they are relevant or not. That is what. Anyway, first question is, I am bothered about the nuclear power plants. Okay, power plant sites, Jaitapur, Tarampur, Kalpakam. I have heard that if you place tetrapods at the shores, then the tsunami probably gets reflected and it doesn't come back again. For example, in Kalpakam, if we had had a tetrapod on the coastline, it may not have inundated the Bhavni pit. This is one idea. So does the model that you are having have any provision for taking into account preventive measures or defenses that might have been built in against tsunami? That's question one. Question two is more fun. That's not anything else. You know, you must be knowing, you might have gone to Mahabalipuram a number of times. In Mahabalipuram, it is heard that from 700 years ago onwards, there have been several tsunamis, and many of the temples have gone under the sea, really. So have you had any idea of tsunamis that might have come? Any historical, have you thought about it, or has it occurred, or is it not relevant? Thank you.
Sir, the first question, as far as the tetrapods are concerned for preventing tsunami, this has to be again a very detailed study. And I think there are various measures that people think of putting, like let us say tsunami wall, building a tsunami wall, or let us say putting a tetrapod. So basically, this all energy gets dissipated once the waves hit the shore. But according to me, and many of the experts also feel, that time we have been discussing, that this has to be done very meticulously, in the sense, let us say that, okay, you protect one facility, but all the energy will be going to a neighboring village or a neighboring facility. So that will get inundated. So, this protection is good, but unless until you do it very systematically, so that needs another kind of study, means basically the fluid structure interaction, or wave loading on the structure, and how that energy has to be dissipated in a manner that there is an even distribution of the energy distribution over a long area, so that there is minor damage. And then again, it will depend on the local flora and fauna, that what you want to protect, what is your priority, and what you can allow to deteriorate or degrade. So this has to be planned systematically. And of course, I am aware that means like not only tsunami, but there are codes which now I think you must be aware that now internationally also many class A cities also get inundated during heavy rains. And so this water management itself is becoming a problem. And I think I have seen some simulations where people do this kind of a study. But in case of tsunami, at least as far as protection of plants or any important facility is concerned, you can protect it by building these tsunami walls or putting some tripod. But you have to also worry about the neighboring areas, because suppose say a village gets inundated, then they will immediately blame that, okay, they are safe, but then we have been suffering. So
Yeah.
this has to also take that perspective in mind.
Yes.
So that was the first question. Now the second question, Mahabalipuram. Yes, there have been, in those days there have been multiple number of inquiries coming, and some documents being submitted to AEC, and then we had to respond. Historically, yes, there have been some. In fact, there is a study by IIT Kanpur group on the paleo-tsunamic events, some 8,000 years of tsunami for this Java Sumatra region, and there they talk about some such, but it all depends on the additional studies are required again in terms of carbon dating, and means what is submerged, and then do some carbon dating, and then only come with a proper conclusion. So I think we need to have a scientific approach to investigate all this. This is what I believe.
I don't know whether they have found the submerged temples. I'm quite interested in that, whether they have been able to get it or not. But anyway, thank you very much, your answer. Thank you very much.
There was a hand by Mr. Avnish. I don't see it now. Mr. Avnish, are you still interested in asking question? Mr. Avnish? Okay. If not, then I will go over to Mr. Manchanda. Mr. Manchanda?
Yeah, yes. Thank you, Dharnaji. Dr. Singh, my name is Manchanda.
I know you, sir.
Oh,
You don't have to introduce me.
Yeah,
You don't know him, but you know him.
Okay, now let me, actually my question, Singh Saab, is more a curiosity actually. The biggest accident because of tsunami in recent time is Fukushima. My question is that, the modeling which may have been done for the tsunami in that area, Fukushima, whether that failed miserably, or in spite of all the warning, nothing could have been done. So that is one part of the question. Am I clear in my question?
Yes.
Okay. The second thing is, as the time passes, we are able to do more better and better modeling. So are there some cases where because of the good modeling, we could do the prediction and avoid Fukushima type of accidents as far as the nuclear power station are concerned? Maybe it is hypothetical, but you can try to address if you think it is reasonable.
Dr. Manchanda, thank you for your query. As I mentioned in my lecture, see, this Fukushima location is hardly 200 kilometers from the tsunami source. So this is one problem with that Fukushima plant, that it is, means, so in terms of modeling, if you see, they would have, means conventionally done some very simplistic modeling of the surface waves and so on. So in fact, that needs a very detailed kind of modeling, and I am not sure whether in that era those kind of capabilities were available. So this is one part. Then I have also some official information that means the designers overruled the people who gave them suggestions. They basically the seismologists and the geologists. They gave some warning that yes, this place is vulnerable because of this tsunami considerations, but they overruled that, and perhaps the plant grade height or the design basis flood that was that was not accommodated properly. So this is what I know from official records.
Okay. I think,
Now,
but can you
No, can you
unshare,
please,
unshare and
no, just 1
unshare?
minute.
Yeah.
Yeah, since
Can you
just 1
please,
second.
Manchanda, just a minute. Since can you unshare and so that we can see each other? And
okay.
participants to
Yeah. I mean, stop sharing your screen.
stop sharing. And I'll request all the participants to unmute your video.
No, I am not seeing that.
See at the
It's on the
just
top.
move your cursor. At the bottom, you will see share screen.
At the top, there is one.
Yeah. Okay.
Green, you can unshare.
There will be a warning at the top that you are sharing your screen. Just move your cursor on the window. Yeah.
Yes.
That's it. Yes.
Thank you. Yeah, so Dr. Manchanda, as I was telling that, means first of all, this location itself for the Fukushima, Tohoku place where the earthquake took place, sea earthquake, that is hardly 150 or 200 kilometers from the Fukushima plant. It is very, very close. So this was one problem. The second problem is with regard to the modeling, is those kind of sophisticated modelings, they were perhaps not available those days. And of course, for doing this, you need a lot of data.
Mr. Dubey, please stop sharing your screen. You have inadvertently started sharing your screen. Mr. Dubey.
So you need, means see, if you see the Google Earth, they have some half-minute grid data of the sea depth as well as the land morphology and so on. And of course, there are security issues with regard to the collection of data. Means fortunately that time with good offices of Dr. Chidambaram, who was principal secretary that time, we could approach NRSA because these data are again in the security zone. Means normally the this data particularly at the important locations, they will not be shared by so we had in fact asked the participants also to take an undertaking that they will not share this data of land morphology and bathymetry further to any, or they will not publish also. So they can publish scientific work but not the data. So that was the agreement. So all these things are required to be done very systematically. And of course, in case of Japan, I think those days, I think it is old plant. So those, I think capabilities may not be available, but now if they are doing a re-evaluation, I hope they must be doing it systematically. Of course, Japan took a lead in this IAEA program also. They shared their code, and Tsunami N2 has come from them only. So
my second part of the question was, in recent times when the modeling whole thing, I mean, this discipline has got polished and improved, whether is there any case where because of the good modeling, we could save some accident, the damage caused by the accident, whether any such case is there in recent time, in last 10-15 years?
I think I already explained about that Madras reactor event, 2012 event, where means in within 8-10 minutes the warning was issued, and means all these things were in place, and they could shut down the plant very systematically. So I think yes, but it means modeling alone is not sufficient, because you also need to have good instrumentation. I will give you example. Many a times, let us say this, I used to get query from the national warning system. That time our late Sri Bhattacharya was in NDMA, that sensors are there but they are not working. That was the one complaint from NDMA. So means it has to be done systematically, in the sense that sensor calibration, and any event, let us say they are monitoring the tide, or they are monitoring the any event in the sea, so they must be doing it systematically, and even let us say some data is being collected, so that should be analyzed. So I think that is the responsibility of the INQUISE Hyderabad. And in fact, I am following that Twitter page of Mr. Srinivas Kumar. So he keeps on writing that, okay, this event has taken place, and means there is a now regular warning given, so anybody can register there and then they can do. So nowadays, of course, this modeling, then communication technology and the sensor technology has improved, but basic sensor technology is the same, and that somebody must look after, and calibrate. In situ calibration is most important.
Thank you.
Yeah, I will go to Dr. Mishra. Dr. S.K. Mishra, please.
Voice clear, please?
Yes.
Yes.
Okay, thank you, Dr. Singh, for giving such a elucidating type of presentation, even for a layman like me. I have more of curiosity. First thing is, what is the normal lead time available? I have worked in disaster management for some time. So there the lead time is very important for responding to a situation. And second thing is, the near coast tsunami and the tsunamis away from the coast, is there a thumb rule which can be predicted, which can be used for prediction about the level of hazard?
What was your first question?
First question is, what is the lead time available?
Okay, lead time, yeah. So lead time will actually depend on the various situations, like means because lead time normally, see, it is not only the distance, but what is the local morphology, what is the sea depth. Like let us say in case of, I will give you example, like lead time available in case of Java Sumatra is normally not that large as compared to the western coast, where the sea depth is very shallow near Gujarat. So there the waves propagate very slow. So of course lead time is more in case. So that is again specific to the sea bathymetry and land morphology. And
I will repeat, whether this is in terms of minutes or hours.
It will depend on the source. Let us say an earthquake takes place in Java Sumatra. So lead time for the Andaman people is very small. It is in terms of tens of minutes. But for Bombay people, or let us say here, we have a lot of lead time. In fact, now I will give you information that INQUISE, moment a event takes place, they start running they have already in their record all the pre-run data cases. So from that, they just calculate, okay, this is the source, and they start giving warning that, okay, this time this will be coming. And of course, they refine the calculations based on the exact magnitude and the exact location of the earthquake source, and they modify that slightly. So nowadays, I think it is just instant. In the minutes, they will give you the information. Then apart from that, if we have the bottom pressure recorders, and through satellite, you get again data immediately. And that is what happened in case of Madras reactor, which I mentioned, that within tens of minutes, they issued the warning.
All right, thank you very much.
Thank you, Dr. Singh. I will now request Mr. Padmanabhan to ask his question. So Padmanabhan.
Yes, sir. Thank you, sir. Thank you for giving this opportunity. Sir, I have one doubt basically. Nowadays, all these nuclear reactors, whichever we are constructed already, now because of their life, and we are going for the reassessment and extension programs. So there is one question, basic question, which is being asked by regulators to reassess the tsunami level or to have the assessment of the beyond design basis level tsunami. So, sir, can you throw some light on how we can evaluate the tsunami level for the beyond design basis events?
See, as far as this deterministic analysis or deterministic hazard evaluation is concerned, that means there has been some discussion with the experts in the AERB. They have already fixed up the magnitude value for the Java Sumatra region, for the Makran region. And I think there was a meeting with Professor Harsh Gupta and other experts in 2016. So there is a white paper issued on that. The magnitude of the earthquakes are known, 9.2 and for the Java Sumatra and 8.1 for the Makran. So that is now the standard given. So based on that, one can carry out this analysis, and already this data is available. So for a space, but when you go for a specific site, then you need to collect additional data of the land morphology and the means I remember for additional facilities being this reprocessing facilities being constructed in Kalpakam again in I think 2012 or 13 let Dr. Basu had asked me to again evaluate that. So we took help of the local instrumentation people. We did some, and SRI, there is already a group which is working on this, and they have all these instruments available. So they do the survey, and based on that they can give you the data, and based on this added modeling, it can be done.
Thank you, sir.
Yeah. Mr. SBT, I don't know the full form because it just displays SBT. You can ask the question, please.
Hello.
Yeah.
Sir, this is Swapnali from NPCI.
Okay.
So it is quite a generalist question.
You can put on your
I just
video,
wanted...
please. You put on your video.
Yes.
I want to take a picture. I request all the viewers to put on their videos. I want to take a picture.
Just a second.
Sure, sure.
All viewers, please put on your videos.
Hello.
Yeah, go ahead.
Good evening, sir. This is Swapnali from NPCIL. So my question is quite generalized. So, sir, due to the lack of historical data, sometimes what we need to do is we need to assume some, we need to do some assumption regarding the inputs. So, that sometimes what happened, we do not know that the assumed value is conservative or over conservative. So I just wanted to know how to overcome the difficulty.
I can give you some example, like I mentioned, I think already, that let us say if you take up the example of Java Sumatra, and let us say that as per the regulatory guideline, there is a requirement of 10,000 return period. So I think IIT Kanpur group is working on the paleo-tsunamic events. They are collecting the samples at various locations, and based on that, I think Javed and his team, they are working on this, and I think already there are some publications with regard to that what could have been the magnitude of those earthquakes. And of course, by taking all these events of earthquakes, past events, including the paleo-tsunamic earthquakes, and of course, you need to do a lot of site survey, means if there are some marks there, or means if you do some survey, then in that case, you will find some additional information. So based on all this, and of course, later on, as it happens in case of this seismic hazard, probabilistic seismic hazard evaluation, like they take a peak acceleration value which is conservative compared to the all past events as well as the future events. So I think I mentioned in my talk that in fact in case of tsunami also there is an approach they call it PTHA, means probabilistic tsunami hazard assessment. So this effort is also going at international level. This is a new study which has been coming up, and in that case, they are ensuring that all the past tsunamis and the future tsunamis which will be happening, they do some logic tree, and based on that, they come out with a tsunami height that is design tsunami, and that will be never exceeded in future, let us say for 10,000 years or so, because means this is important. So this is what is the state of art.
So one more small question, sir. With time, the data resolution is also improving. Like, do we need to reanalyze that what we have done already is with the resolution of data, improvement of resolution in data, or that it is not required, sir?
If you have improved data, at least you should reanalyze and ensure that whatever you predicted was conservative at that point of time. And now, of course, that is a reassurance of your work.
Yes.
But I think again, it will depend on the specific cases. Means this is just a general comment which I have given. Means unless until I know the details, I cannot really address this.
Okay. Thank you, sir. Thank you.
Thank you. Dr. Prasad, your question, please.
Good evening, sir. I would like to know this. Recently, there is a a talk going on installing nuclear plants in conventional thermal power plant sites. Whether any additional requirement is there, like tsunami evaluation, modeling, other aspects for these sites?
If it is a coastal site, then of course it will be the same procedure that has to be followed. But if it is not coastal, then I think we don't have to worry.
Dikshit sir, you have any question?
Okay. Anybody in the audience has a question? Yeah, Srilata.
Muted, yeah.
Srilata, go ahead. Srilata, your voice is not coming. Yeah, your voice is not coming. She's not muted. She is okay, but your voice is not coming. Just check your connection. Yeah. No, not yet. No. You can put it in the chat.
Put it chat box, yeah.
Yeah. Yeah. Till then, we can look for another question from audience.
Yes, sir.
Hey, Malhotra, you normally ask questions. Malhotra ji.
Yes.
Yeah, very good evening, sir. Very good evening. This is a very relevant topic you raised. Already he has discussed many things for the nuclear power plant which are being seen by ARB guidelines. Sir, Visakhapatnam site of BRC is coming up where are two major facilities of accelerator complex as well as the HFRR reactor will be coming up. Now this accelerator is already in a tunnel which is again below the mean level, sea level or the DBFL. That has been considered. Do you believe that tsunami breaker thing should be implemented at Visakhapatnam site? And these days it is Visakhapatnam site is it has a hill also, and natural channels water flow need not be disturbed. So are this being considered now?
Can I request others to unmute themselves?
Mute themselves.
Yeah,
okay.
mute themselves.
First of all, I think Vizag site also, I think in 2012 or so it has been, or 2013, I don't remember exactly, but that was the last site we evaluated. And the results are available in form of a BRC restricted report already. So perhaps you should look at that. But again, your question is very specific. Unless until that site is known and some details are not, I cannot comment. And I already replied one thing that means to Mr. Sanat Kumarji's question that means if you want to protect some facility, you build some wall or anything or any protection measure you have, the energy is fixed. So finally this energy has to be dissipated evenly around that area in a systematic manner. So that is very important as far as the plant layout is concerned. So that has to be seen in more detail.
Yes, sir. Yes. Second, I have one more supplementary, sir. These waves carry that energy that you rightly mentioned, and the shallow fields will have higher impedances, so they will they will at least slow down the tsunami. Second thing, are there any concerns with the wake fields? In the wake of this large wave coming, are there certain vortices which are following it, like a wake field of a, say, Dreamliner? A Dreamliner leaves in its wake a lot of vortices. What happens to that part?
Yeah, your question is again very specific, because you have to see the wake structure, the vortices and other things, and depending on that, because unless until I have more details, I cannot perhaps comment. I cannot make a general comment. So that needs.
Yes. Yes, sir. These wake fields these days are used as an accelerator. You see the wake itself. So that was the yeah. So I was just.
As I have mentioned, that there is already a BRC this restricted report in library, so you can perhaps have a look with whether that addresses and some additional work if that is required. So that I think with experts that can be.
Sure, sir. बहुत धन्यवाद, sir. Many thanks and wish you all a good. Thank you.
Dr. Singh, there is that question from Sri Lata is here in the chat. She says that this is with respect to probabilistic tsunami hazard assessment, as we were talking about it. And she says, in the absence of historic data, how such assessment can be taken up? She wants some guidance on it.
Yes, data is always a problem. And so I think, means there is also a requirement that, means all the experts, they gather together and then they give some expert opinion and expert elicitation. So from that, a convergence can be achieved, and then based on that, one can move forward.
Yeah. Mr. Pahadi, can you raise your question?
Santanu.
Yes, sir. Yes, sir. Good evening, sir.
Good evening.
Sir, actually, my question is, so far the work done in this field of tsunami prediction, and for utility, actually I am from NPCIL. So for utility, if you can guide me, what are the work ahead, or where should the utility focus now, as for say for the future decade, where the utility should focus, especially on the tsunami prediction. One might be that probabilistic assessment that already have told. Any other field, sir?
See, as I mentioned in my talk already, means the probable sites, we have some, first level data that is available, means what is the wave height. So that input is already available. Now let us say tomorrow Jaitapur or Haripur or any other site is coming. So we should have a detailed map of that area, the bathymetry and the land morphology. And based on that local modeling, and already I think that there is a good team already available. So one can organize that and carry out the assessment systematically. So this is what I feel.
Okay, sir. Thank you. Thank you very much.
Yeah, there are two more questions, Dr. Singh. One is from Thangavel. Dr. Thangavel is asking, is it possible to predict the forthcoming tsunami prediction based on the past and paleo tsunamis?
Yes, this is also, important discipline. Geologists and geodesy people, they keep predicting. So based on the paleotsunamic studies and these kind of, means detailed in-depth studies, they predict that, but still I think that is a very, very gray area. So I think if you look at the extreme event, or let us say, so in that mostly the probabilistic or the predictive aspects are not taken into account. Means let us say in past 9+ magnitude earthquake has taken place. So we assume that and we design our facility and be ready for that. So that is the most conservative approach. And that is what was done for the Kudamkulam site. Means we assumed even for the Makaran that 9 magnitude, although there is a decision by the expert that 8.1 or so, it will not be exceeding. Similarly, for the Java Sumatra 9.2, more than that is not possible. But still, I think people do that.
Thank you, Dr. Singh. There is one more question from Dr. Gopal Venkateswaran. Is there any definite frequency for tsunami resulting under sea earthquakes, or do they occur randomly?
See, this actually needs to have a look on also the various fault parameters and the so this is a subject basically means again in the prediction area, means it is not possible. See, like we are hearing Himalayan earthquake, it will be now any. So they are mentioning that 1934 Bihar Nepal earthquake, or before that also there was an earthquake. So they are saying that again 100 years later you must be saying in the newspaper Uttarakhand will experience that and Delhi will be affected. So these are again means very, very gray area. So earthquake predictions as such means there are some papers available which you can predict only in, let us say, if earthquake is coming in a few minutes, or in case of half an hour or 40 minutes, not before that.
Yes.
Of course, there are theories, there are experts who are differing in opinion. So best possible route is to design your facility in such a manner that even if, let us say, this extreme event happens, then at least your plant is protected, people are protected, and you don't lose the faith of the public. So according to me, for any developing country like India, if we have to march ahead, we have to ensure on, means basically they should have believe in the engineers and scientists that yes, at least they have taken care in the plant design, such that even if, let us say, because these events, let us say, because moment we go to the extreme events, we don't take probabilistic aspect, and this is the viewpoint, means we say that yes, this has happened. Now what is whether the public can be protected, whether there is any requirement of the relocation that can be avoided. So if we are ensuring that, then I think technologically we can progress.
Okay. Thank you, Dr. Singh, for answering each and every question, and the range was quite a big range from prediction to actual modeling part of it. So thank you so much, and I hand over back to Dr. Ramarao.
Yeah, thank you, sir. Thank you, Dharneji. I once again thank you, Dr. Singh, for giving us this opportunity to listen to your wonderful work. It was my long desire that I should call you, but then before our tenure ends, that happened, and I'm very happy about that. I thank our President, S.K. Mehta, who is always present in all the webinars to encourage us. I also thank Executive Committee of INS for encouraging this scientific work. I thank Mittal and Sri Simjit Rajgopal for circulating the information to all the members. Normally, I inform about the next webinar, that is my practice, but then our tenure is ending now. So elections are going on, and I don't want to take a chance. The next person will take forward this. So I reserve that. If at all there is any, this will be intimated to all of you. So I thank each and everyone, particularly the viewers, for participating in this discussion and making it lively. It has been very popular, the way participation is seen today. Thanks to Singh for his exciting topic of discussion. Thank you all. Now you take your permission to stop the recording and also stop the